In this next sequence, we will cover nonlinear circuits. The reading is chapter 4.1 through 4.3 in the textbook. Nonlinear circuits contain one or more nonlinear elements, and these elements are different from the linear elements that you've seen so far. A nonlinear element is one whose VI relation is nonlinear. So, for example, if I have an element whose current I relates to the voltage across its terminals as some constant times V squared, would be a nonlinear element. So in this sequence, we will cover such elements and circuits built using those elements. Okay, let's start with a review as usual. We started this course by discretizing matter and developing the lumped circuit abstraction. Our first step was to create a tool chest containing several analysis techniques, and we've looked at 5 techniques. Okay, method 1 was the what we call the KVL-KCL method, and in this method, you combine KVL-KCL relationships and the IV relation for all the elements in the circuit, put them into a big hopper, and ended up by having to solve a set of system equations that eventually gave rise to all the voltages and currents for the circuit. Our second method involved composition rules, where you use simple addition, subtractions kinds of analyses to compose resistances and sources together. A third method, which I said was the real workhorse of our business, was the node method. And by and large, we applied this method to most of our circuits. We then covered methods 4 and 5. Method 4 was the superposition method, and method 5 were the Thevenin and Norton dual methods. Now recall, if you look at the first 3 methods, these methods apply to any circuit. However, if you look at the last 2 methods, the superposition and Thevenin methods, these apply to only linear circuits. And so when in doubt, go ahead and use the node method, but the superposition and Thevenin methods are extremely powerful. And what is interesting about these methods is that you can apply these methods to linear sub-circuits as well. So if you have a big circuit, and then the whole big circuit may contain linear or nonlinear elements, you can carve out, if you have a big circuit like this, and it could be an arbitrary circuit, but if you can carve out some part of the circuit that is linear, then you can apply these methods to that sub-circuit as well. We will use this trick in some of what we do today. Continuing with our review, after we built the lumped circuit abstraction by discretizing matter, we continued with this method of discretization, and we discretized value. And by discretizing value, we came up with the digital abstraction. So in this abstraction, we treated values as we use ones and zeros as the values in the circuit, and just looked at highs and lows. Okay, we didn't care about intermediate values. And this gave us the key property of noise immunity, which really enabled us to build very large circuits and systems that worked consistently in many noisy environments. One of the interesting things to note with the digital domain is that it is very tightly coupled to analog design. Again, the two are really, really very close to each other, and the foundations of both are the same. And one thing to notice was that with digital circuits as well, sub-circuits for a given switch setting were all linear. So in other words, if I took a circuit and I established some switch values, and then for those fixed switch values, I ended up with circuits that were linear for the kinds of switches and kinds of elements that we had talked about. And once you have that, you can apply any one of the 5 methods that we discussed so far to those circuits. So just as a quick example, supposing I had this circuit, and recall this circuit is a NOR gate, A, B, and C. And this is a NOR gate because the output C goes to 0 if either A or B are a 1. Okay, if A is a 1 or B is a 1, the output is going to go to 0, and that is reflective of a NOR property. Okay, so that is a NOR gate. Now, if you look at this gate and apply the switch resistor MOSFET model to build an equivalent circuit for this gate, then what do you see? So supposing I use my switch settings A equals 1 and B equals 1, okay, both are high, then you will get the circuit seen on the right here. This circuit is a sub-circuit that you get. And notice this sub-circuit contains a voltage source and contains 3 resistors, so this circuit is linear. Then I can choose a different set of switch settings, A equals 1 and B equal to 0. And so for that, here, the B input MOSFET is turned off, while all the others are RL, and the resistor RL is of course there, and the MOSFET connected to A is also on. So notice here that this subcircuit is also linear. So the beauty of this is that in the digital domain, for the kinds of circuits that we've built and the elements we've used, for any given switch setting, the subcircuits that I ended up with were also linear, so I could apply all my linear analysis methods.